Today, I'm going to work with you on a new concept, and that is the concept of what we call electric field. We spent the whole lecture on electric fields. If I have a charge, I just choose Q, capital Q and a plus at a particular location, and at another location I have another charge, little q. I think of that as my test charge. And there is a separation between the two, which is r. The unit vector from capital Q to little q is this vector. And so now I know that the two charges, if they were positive, let's suppose that little q is positive, they would repel each other. Little q is negative, they would attract each other. And let this force be F. And last time we introduced Coulomb's law. That force equals little q times capital Q times Coulomb's constant divided by r squared in the direction of our roof. The two have the same sign. It's in this direction. If they have opposite sign, it's in the other direction. And now I introduce the idea of electric field, for which we write the symbol capital E. And capital E, at that location P, where I have my test charge little q, at that location P, is simply the force that a test charge experience divided by that test charge. So I eliminate the test charge. So I get something that looks quite similar, but it doesn't have the little q in it anymore. And it is also a vector. And by convention, we choose the force such that if this is a positive test charge, then we say the E field is away from Q if Q is positive. If Q is negative, the force is in the other direction, and therefore E is in the other direction. So we adopt the convention that the E field is always in the direction that the force is on a positive test charge. What you have gained now is that you have taken out the little q. In other words, the force here depends on little q. The electric field does not. So the electric field is a representation for what happens around the charge plus q. This could be a very complicated charge configuration, and electric field tells you something about that charge configuration. The unit for electric field, you can see, is newtons divided by Coulomb in SI units. And normally we won't even indicate the unit. We just leave that as it is. Now, we have graphical representations for the electric field. Electric field is a vector, so you expect arrows. And I have here an example of a charge plus 3. So by convention, the arrows are pointing away from the charge in the same direction that a positive test charge would experience the force. And you notice that very close to the charge, the arrows are larger than farther away. That sort of represents, is trying to represent the inverse R square relationship. Of course, it cannot be very quantitative. But the basic idea is, this is of course spherically symmetric if this is a point charge. The basic idea is here, you see the field vectors, and the direction of the arrow tells you in which direction the force would be if it is a positive test charge, and the length of the vector gives you an idea of the magnitude. And here I have another charge, -1. Doesn't matter whether it is -1 Coulomb or minus micro Coulomb, just it's a relative representation. And you see now that the E field vectors are reversed in direction. They're pointing towards the minus charge by convention. And when you go further out, they are smaller. And you have to go all the way to infinity, of course, for the field to become 0. Because the 1 over r square field falls off, and you have to be infinitely far away for you to not experience, at least in principle, any effect from the charge. What do we do now when we have more than one charge? Well, if we have several charges, here we have Q1, and here we have Q2, and here we have Q3, and let's say here we have Q of I, we have I charges. And now we want to know what is the electric field at point P. So it's independent of the test charge that I put here. You can think of it, if you want to, as the force per unit charge. You've divided out the charge. So now, I can say, what is the E field due to Q1 alone? Well, that would be, if Q1 were positive, then this might be a representation for E1. If Q2 were negative, this might be a representation for E2, pointing towards the negative charge. And if this one were negative, then I would have here a contribution E3, and so on. And now we use the superposition principle, as we did last time with Coulomb's law, that the net electric field at point P, it's a vector, is E1, influence of charge Q1, plus the vector E2, plus E3, and so on. And if you have I charges, it is the sum over all I charges of the individual E vectors. Is it obvious that the superposition principle works? No. Does it work? Yes. How do we know it works? Because it's consistent with all our experimental results. So we take the superposition principle for granted, and that is acceptable, but it's not obvious. If you tell me what the electric field at this point is, which is the vectorial sum of the individual E field vectors, then I can always tell you what the force will be if I bring a charge at that location. I take any charge that I always will carry in my pocket, I take it out of my pocket, and I put it at that location. And that charge that I have in my pocket is little q. Then the force on that charge is always q times E. Doesn't matter whether q is positive, then it will be in the same direction as E. If it is negative, it will be in the opposite direction as E. If q is large, the force will be large. If q is small, the force will be small. So once you know the E field, which could be